Good afternoon and welcome to our second project show for today. We have a team LDMS for Life from the University of Bern, and they will tell you where and how do we search for the signs of life on the extraterrestrial bodies. Thank you very much for joining us today. If you would like to know more about the project, please use our YouTube chat to submit your comments and questions to the team, and we will have some time after their presentation for a discussion. Now I'm happy to give the word to the team.
Hello, good afternoon, everybody. My name is Koen. I am the project manager of project number 14, LDMS for Life, like Maria said. And also, as Maria said, the thing that we've been focusing on for the last 6 months is how to find and where to find life outside of Earth. And today I want to be talking to you a little bit about that subject and show you what we've been doing over the past months. But before we dive into that, maybe to answer a question that many of you might have had in their head when you hear searching for life outside Earth is why? Why would we spend so much time and money and energy to search for life outside of Earth? And well, there are a couple of answers. I mean, of course, we are biased because we think it's an absolutely fascinating topic. But maybe it's good to realize for everyone that exploration in any kind has always been part of human nature. We've explored every nook and cranny of this Earth, and yeah, it's time to start looking outside Earth to find boundaries of living species not on this planet. And aside from this interest in it, you could also realize that the technologies that will be developed to help our search for life are things that could very, very much help us here on Earth. So it's not just a philanthropic endeavor. So to search for life, we need to have a bit of a strategy, because it's not as easy as just flying somewhere and shouting about, hello, is anyone there, and hoping for an answer. So what we need are what they call biosignatures, which are markers, chemical or biological markers, physical markers that indicate the presence of life. This can be both life that exists right now, so that's living right now, but it can also be life that has been extinct for years, decades, even millennia, up to billions of years. And so the astrobiological community, as this is called, they decided on a couple of biosignatures, and they range from very big scale, so rocks and lamination in rocks, which you could see by eye, to very, very small things like chemical signatures. And these are the ones that we will be focusing on, such as organic molecules, but also isotope ratios, so the ratio between different isotopes of the same element. So what do we actually need to search for this? Well, we need two main ingredients, let's say. We need the team, which in this case is us, and we need the tool, which is the instrument that you will see, that you now see on the right. So we are a team of 5 students, postdoc and PhD students, working from the University of Bern in Switzerland. And over the years, the group in which we work has developed a very interesting and exciting new tool to look for biosignatures. And this is actually what our project focused on, and what we will be sharing with you today.
So our department is, since decades already, since the first experiment on the moon on the Apollo 11 mission, highly involved in space exploration, in space research, and the development of new measurement techniques and instrumentation. We are involved in many current space instruments, but also very recent one, like the Rosetta mass spectrometer, the RTOF we had on the Rosetta mission. But we are also involved in many on the ongoing projects, like the Pepe Colombo mission to Mercury, with here the Bella instrument or the Strophio instrument. And maybe you heard very recently that we are also involved or providing, we have the lead with the Cheops mission, where we designed everything independently here in-house, a 30-centimeter telescope designed to search for exoplanets and also to investigate known bodies in more details. So before I go in more details, we will show you now a movie which we pre-recorded with the director of our Space Institute, but also the PI, the director of the Physics Institute. They are well-known leads in planetary missions. And now I pass by to show the movie.
I was 8 years old when Neil Armstrong first walked on the moon, and so I was always interested in space from a very early age.
Well, I was always fascinated by designs for extreme conditions, for extreme applications, so I first went into motorsports, and afterwards I ended up in space, and that's it.
First, I didn't know that you can become a space engineer in Switzerland. I thought that there was no industry, no institute that would do space stuff. When I discovered that you can, I started to orient my studies towards it, and then I was lucky to find a job here at the University of Bern, and I've never looked back since.
When I came here, I was hired for the SOHO project, the Solar and Heliospheric Observatory. I came late to this project, hardware was almost built, so I was hired more or less as a project manager to finish the hardware, organize tests, conduct the tests outside at ESA premises, at NASA premises, all the way to the launch campaign.
My first involvement with a space-related project was, I would say, the vibration test of Bepi Colombo hardware here on the shaker. And Bepi Colombo took off by the end of 2018 and is now flying towards me.
There's a drive there purely from a managerial point of view to keep acquiring new projects. But of course, there's also fundamentally, I'm interested as a scientist in looking at new missions and looking at performing new science.
Space projects are always interesting because they are never one like the other. Every time you have new boundary conditions, new objectives, so this is a great motivation for an engineer.
What the opportunity you have in space missions is to address big questions about our solar system, maybe beyond the solar system, outside. So questions like, why is the Earth looking like this? How does the Earth work? How does Mars, Venus work? Why are we different from Earth?
I think the first point, when you can work on something that will fly to space and help push the boundaries of what we know about space, about objects in space in the solar system, that's very passionating and very uplifting. subject of work. And the second thing, on the shaker here, sometimes we do destructive vibration tests, and then in the end you get paid to destroy stuff, and that I find really cool as well.
Resources of all kinds are a challenge. So you have limited time to realize this project. You have limited money, you have to build your instrument for the scientific questions you want to address. With limited mass you can put on a spacecraft, with limited power resources you will get from the spacecraft to operate your instrument.
I think a very challenging aspect is the environment that space is something that we don't have here on Earth. So to test the hardware that we create, we have to recreate those conditions, and the infrastructure and everything that you need to do to recreate those conditions is very complicated and expensive.
Well, it's all about people. If you have the right people at the right place in the right moment, then the project will be, let's say, not simple, but by far not as difficult as the contrary. Technical problems are much easier to solve than wrong people at the wrong place. Space project can be stressful, of course, because the schedule is always tight. You can encounter problems, that's normal.
I would say quite stressful. You have to be able to handle stress, you have to be able to handle time pressure, budget pressure, you have to handle failures which come regularly because you're pushing to the limit.
It comes in phases, so early in the project it's not very stressful, but the closer you get to the delivery date, when you need to send the stuff you've done, the more stressful it gets.
It can be stressful in several areas, and there are times when it's fun and easy.
If the project is started in the right way, you have a good architecture, a good team, then it's not so stressful. A sample return mission is still on my wish list. This would be a nice thing to do before my retirement.
For me, and not just for me, finding life somewhere else in the solar system is of course a major goal, the big goal we are working towards.
Out of the list of questions that I was provided with, that is probably the hardest to answer. So I think probably the take-home message I would give you is that persistence and perseverance are very important aspects of the whole process, and if you can bring that to the table, it's good.
The questions we want to address are much broader than can be covered with a single discipline. One has to be open to learn from the others. One has to be open to establish this communication with different fields of your expertise.
I would say it's first of all, it's very gratifying to work on something that flies to space at some point, and secondly also that working to help humanity understand more about the universe is also something that I find personally very enriching.
The most important thing in space projects is really enthusiasm. There's no routine, there are standard processes, but everything is new every time. So you need enthusiasm, you need interest in new things, in new developments. That's the key. And then space will be the right thing for you.
Okay, hello back again. I hope that you enjoyed our movie, the pre-recorded movie. It was actually very fun to record that with the different person. And we can now actually go on and bring a bit closer to what we are doing with this Origin instrument. It's a new system we designed in the course of the last 2 years, I would say, to have a new instrumental setup, what you see on the left side. What we have to mention at that point, it looks very big. One side is about 1.5 meter in width. So this is actually just used to test and to simulate the space environment where we have our system to be operated. So actually the system, what we are using is the one you see here on the right side. It's also that one I show you here, maybe in the hand. So it has the size of a PET bottle. So it is a super compact system, and it's simple in slide weight and can be used straightforward, which I would like to explain you in the next couple of slides. As I said, it's a very small miniature system, and for comparison, we just added here, it's not a branding advertisement from GOP, but it has about the size of a 1/2 liter PET bottle here shown at the right side. So the length is about 160 millimeter in length, 60 millimeter in diameter. The whole system, a flight version, would be about 2 kilograms only, and that includes like a laser system. I will explain on the next slide. We have about 15 watt power consumption, which is low. And one of the main capabilities of our system, it has the measurement capability to detect single ions or larger molecules. So we are very, very sensitive, and we are sensitive for detection of life. So on the next slide here, on the right side, what you see is actually a schematics, how this system is working. It looks very complicated. I don't want to go into this detail, but actually from scientific point of view, it's very straightforward. What we are using is a laser system, a pulse laser system, which produces 20 pulses per second. The laser pulses are forwarded with mirrors that are reflecting the pulses towards our vacuum chamber, where we have the space environment. The laser pulses hits the sample surface, where we take off shot by shot a little bit of material, and then this ablated material we can analyze afterwards in our miniature system. And from that point of view, we have the full chemical information for every laser shot we apply to the surface of interest. So that allows us actually to find maybe life.
So now Andreas has told us a bit about what we want to use and how we want to search for life. And so the next step is to ask yourself, where do we want to search for life? And actually already within our solar system, we have two very promising objects. The first of one, which you see here, which is Mars. Mars has a couple of very interesting characteristics. It's within the habitable zone, which is the radius around the sun, where it's the right temperature for water to exist. It has an atmosphere, which is very unlike many of the planets in our solar system, which is, of course, we believe, very crucial to host life. We know that there's water on Mars, very similar to Earth. The north and the south pole of Mars are covered in large sheets of ice, water ice, which you can see on the right side of the screen. And it's relatively warm compared to other solar bodies. There's, of course, one big minus, one big con, and that is that it has a very, very strongly irradiated surface, which is detrimental to any life that might exist or have existed there. And so the current idea is that if life is or was present on Mars, is that it's probably present underneath the surface, where it's shielded from this irradiation, and either signs from extinct life that have been hidden there and preserved there for a very long time might still be present, or we might even find life ones. The second target was to be at least a bit more of a surprise, which is Europa, which is a moon of Saturnus. And recent flyby missions have confirmed that the shell of this moon is a very thick layer of ice, several kilometers thick water ice. And the idea is that beneath this ice is liquid water. And this liquid water is even thought to be in contact with the very hot molten core, which would provide a lot of energy to the water and also different molecules. So very much like the hydrothermal vents, which you find on Earth on the bottom of the sea. These might be habitats for different types of life things to live. And then through cracks in the surface of the ice, this water might be eject it towards the surface where it then freezes and where it would be very, very easy to detect. Now, the third thing that we need to take into account is how we actually want to search for life. What is the strategy? And currently there are two main, let's say, streams. The most straightforward one, the one that you can most imagine, is a sample return mission, where we send a certain rover or robot to a planetary surface, where it will collect sample material and prepare it for transport back to Earth. And then eventually this material needs to be sent back to Earth, where it can be analyzed to see if it contains anything. Such a strategy is actually being developed right now for the next mission to Mars by NASA. Now, of course, as you can imagine, this is very, very complex. It needs a lot of different techniques, and everything needs to work perfectly. And in the end, you only have the material back on Earth which you happen to select. So it's limited, and it's very, very expensive. And so the second stream, and the one that we prefer, is what we call in situ analysis. And basically, this means that you do your research on the planet itself, and in this case, you only have to send back your results, which we believe is a bit more viable. So that brings us to our objectives for this IGLUNA project. We had a twofold project. On the one hand side, we wanted to show and improve the scientific capabilities of the Origin system. And the way we do this is to show in the lab that it's capable of performing measurements on chemical biosignatures. The second part of our project was to bring the science behind their system, which we can understand is maybe a bit abstract for a lot of people, to bring this closer to the people. So the way we wanted to do this is to create an interactive model of a possible future space mission, which would host our instruments, so that we could show to the public, to anyone who was interested, what we believe our instrument could contribute.
So, and that brings us actually to the next slide, how we are looking with Origin for signatures of life. I mean, I showed you on slides before how the instruments actually is working. But for what we are looking for specifically with that instrument, so let's assume we have kind of life out there, maybe microbes. This is also a discussion at the moment. When we would have microbes, we would have for sure fragments. If the microbes are not even there anymore, so they are degraded because of environment, radiation, etc. For sure, we have leftovers of proteins which are made of peptides. And when we have that, we come actually to the signature we are looking for with our system, and that's amino acids. So we know from Earth, from the life we have here on Earth, that amino acids are very, very important, let's say, building blocks of life as we know it from here on Earth. So we are looking for sure for something outside Earth which we understand, and that's the amino acids, for instance. And so we would go with with our system there, here shown with this image at the bottom, maybe on the rover. At the top of the rover, you see our small instrument at the very front of, at the arm. And then we start our analysis, where we shoot continuously laser pulses to the solid we may think that hosts life or hosted life. So what we are doing actually, we record, as I said before, the chemical fingerprints, and we do that on the biomolecule basis. And what we show here, that looks a bit chaotic to a non-scientific eye, but what I can tell you here as a take-home message is, for the very interesting amino acids we investigated, we find a very unique amino acid signature, which allows us to say, okay, we have this amino acid found, but furthermore, we also can tell you, or the science community, at which concentration this amino acid is present in the solid investigated. And together we have a close picture, which allows us to say indirectly, okay, there was life.
And that brings us to the second part, the second goal that we had during IGLUNA, which was to build a rover. And this rover would host Origin, and we could use it to show the public what we do. And to show you what the process was in getting this, and how it came about, I want to show you a little movie. So that's what we're going to do right now, and I hope you enjoy it. Welcome back, everyone. So there you see it. The rover, as you can see as well in this picture, is ready and ready for doing any type of outreach event and trying to convince people that what we have here is a very interesting and high potential technique. And with that, I think we have come to the end of our presentation. So now it's time to give the word back to Maria, and maybe you have some questions.
Thank you very much for your very interesting presentation. I see that the audience was really excited to learn more about searching for life on other planets and other places in the universe. So I have a lot of questions from our YouTube chat on that topic. But before we go to that, somebody was also asking about the project itself. So what was the most fun highlight that you had during the project?
Well, I guess we could both answer this separately, maybe. So I think for me, one of the biggest highlights was learning a lot of new things. So for instance, to develop the rover, we needed to learn how to design things in 3D sketching programs, and to learn how the 3D printing then works, to see what type of things work and what type of things don't work. So for me, the biggest highlight was for sure that after a couple of months, I realized that I gained a new skill, which I had never imagined that would happen.
Yeah, for me personally, it was clearly, I mean, I'm since working now almost more than a decade in space instrumentation, so I like the project very much. One of the highlight from my personal point of view was really, we were at the end forced, or not forced, but we had the opportunity to print and design our own rover. So I give you an example. We received a 3D printer. We never printed by ourselves. No single print, and we got the printer at the end of February. We printed until when last week about, and we had the first test last week on Saturday, and it worked smoothly. Yes, and I believe that was my personal highlight, that this was like on the point. It worked out.
Well, that's great to see that you had a lot of fun with the project itself. So now maybe let's go with the questions regarding the searching for life. Somebody is asking, can you provide a good assumption on when we will find the life outside of Earth?
Yeah, of course, this is a very difficult question to answer, because it depends on a very large number of factors. The most easily imaginable being how many missions will actually be sent in the upcoming decades. If we send one mission every 100 years, then of course it will take a long time before we find it. And if we send one every week, then it will be faster. So yeah, it's very, very difficult to make an accurate assumption. So I wouldn't try to do that, because I think the chances of me being wrong are astronomical, and the chances of me being right are miniature, let's say.
Yeah, and we have also to say that with every mission we learn something more. Right? Before, when we sent the first mission to Mars, we looked for life on the surface. Now, with the upcoming missions, we know that maybe the subsurface environment is more habitable for life as we know it. So with every mission, we increase our knowledge, and with every mission, we can more or specifically look to a certain indicator of life.
Speaking about the missions, do you think that once we detect the signs of primitive life, let's say on the moon or on the Mars, would it be possible that those are actually the ones that were brought from Earth with the astronauts, with the equipment?
Yes, of course, this is a very, very large topic anyway in space research. The planetary protection program focuses on exactly this, how we can be absolutely 100% sure that we don't contaminate any of the surfaces that we land on. So it's safe to say that basically everything that we can imagine to be done is being done to prevent this. But yeah, I know from the moon there is an anecdote of a space mission which might have already inoculated the moon with Earth microbes. So of course this will be it will be interesting to see. But I think even if we do get, let's say, false positives of microbes that were deposited by humans on let's say the moon, because I think that's the only reasonable where we can expect it, we would still be able to tell that it's life that originated on Earth, because I don't think we should expect life on the moon to be that similar to life on Earth. So maybe that we can then use to distinguish between the two.
I would like to continue on this topic, speaking of false positives. Regarding the technique itself, what are the chances of receiving the false positives using your technique, and how do you study this question?
I guess that's you.
Okay, I can go on. Yeah, false positive detection is really a critical point here, and many thanks that this person addressed that question to us. It has a lot to do with a lot of instruments we had on previous missions to, let's say, Mars, right? In this missions, in the recent missions, we had a lot of sample preparation as well, which may alter during the analysis the solid we are interested in to analyze. And that was one of the big discussions we had all the time, and we have really to make precautions on that. Now, taking our instrument specifically for that, it's important also to address that we are not looking only for one single amino acid, right? Because maybe that's just by chance we found something. So we are looking for a pattern we investigated, which is very important for life as we know it from Earth. So when you have already, let's say, a couple of amino acids, 5, 6, 7 amino acids, which show up at high abundances, that is actually our indicator, and that reduces these false positive detections dramatically. So this is just concerning our instrument. What happens actually on space missions is it's instrument effort. So we deploy many instruments on a planetary body to answer this question. So if only one instrument shows the flag of we found something and the other not, so the discussion starts. So we need to have like a complete set of sophisticated instruments answering that question, that we are sure we found something or not.
Thank you. I guess you convinced me, and hopefully the audience as well, that with this technique, the false positive should not be such a big problem in terms of the technique itself. But then I have another question. So what about the life itself? How do we know that the life on other extraterrestrial bodies would follow the same rules as life here on Earth? So what about the false positives in that sense?
Yes, I guess, but at that point, this is fully true. We don't know what life will look like. We have no idea if it will follow the criteria that we are used to from Earth. But at least in my opinion, the problem there is a bit, of course, is a valid point, and we might even get false negatives because we search for something that simply isn't there, because the life that we are looking for uses completely different. For instance, they could not use amino acids, which is something that we cannot imagine, but that doesn't make it impossible. But the problem is a bit there that we don't know. So we cannot look for something that we cannot imagine. And so the best effort we can do is to look for something that we believe is viable, vital, and yeah, essential to life, so that life could really not do without it. I guess that's about the best effort we can do.
This was a very nice part of the discussion. Now I would like to address some more technical questions that we also have from our YouTube chat regarding the current project itself. So now you presented the rover with the payload, so to say, as a mock-up for interaction with the public. But now thinking about the future real missions and your instrument, what would be the best place to put the payload on the rover so that it is protected from the dust and the radiation?
Well, I guess I look over to you.
Sure. So we addressed that bit during presentation, we agree. And if I could choose a mission which I like the most, would be a Europa lander mission, because there we have like ice samples with the new observations we have, as Koen presented. We have these liquid oceans, we have these thermal vents at the core, or where at the interface between core and ocean, where life may exist. And when we would have the chance, this would be the goal, to have our instrument on the payload of such a mission.
And I think concerning maybe the place on the rover where the instrument should be to be protected, I think the current plans for missions like that is that the entire instrument suite, like Andreas told before, will always be housed inside the rover or lander, behind many protective shields and samples that will be drilled from the surface by some sort of drill collector would then be fed to the instrument suite as a whole. And so that automatically would mean that the rover, not like on our model, is outside and outstretched and vulnerable on an arm, but somewhere inside and protected. And actually, during our discussions on how to design the rover, we passed this point many times because we wanted to be as realistic as possible. But of course, it's a bit difficult to do to place the instrument inside the rover and then try to convince people, yeah, it's really in there. So just for visual purposes, we now place it outside, but realistically, it should be inside.
Now that you mentioned your ideas on the design of the rover and how realistic it is, I have a question. I think it is related to this. Somebody is asking, could a rover with this type of tire, so small, move on the uneven surface of the moon?
Please go ahead.
Yeah, well, actually, that's a funny thing, because maybe for the space enthusiasts, they might have recognized it, because it's a 1:2 scale model of the MERB rover, the Mars Exploration Rover B. So actually, it's a rover that has driven on the surface of another planet, in this case Mars. I'm not 100% up to date on let's say topography of the surface of Moon versus Mars, so I'm not sure if the terrain would be much rougher, but I'm assuming that it should be no problem. Of course, scaled up to twice the size.
Yeah, I mean, the Curiosity rover at the moment we have on Mars is like a car, right? Keep in mind, so this is something very big. It looked here small on our image, but this kind of instrumentation, like now on Mars, they are car size.
Thank you for your answers. I have a very technical question. What is the communication latency limits for your rover in a real-time lunar mission?
Oh, that's a good point. That's a good question, and that depends highly on where we have our instrument, right? So what we can say is typically space instrumentation on rovers, they almost operate autonomously, right? That we actually, to solve that problem, that we not need to interact all the time. So we give the instruments jobs to do, right? And as soon as we started the job, typically all the instrumentation know exactly what to do and they deliver data. Then the data is typically, depends on the orbit where we are, right, is then sent back to Earth, and then we have pre or like post data analysis in the labs. So the instrument on the rover is typically working autonomously.
Thank you for your answer. A more general question, if you could remind us a short maybe overview of the similar existing technologies, similar ideas for searching for life.
Yes, at the moment, that's a good point. Maybe that's even a person which is involved in this project. We have a laser desorption mass spectrometer on MoMA, which will fly to the Mars as well in the near future. It's also a laser desorption mass spectrometer, but coupled to very different instruments, right? This will be one of the closest, I would say, what we are doing. I would also like to keep in mind the instrument that's like this 3D print here was already on the called LASMA in the past and was also part of the Phobos Grand mission. Unfortunately, the spacecraft died in the orbit after we left the Earth, which can happen, right? But I would say these two instruments, this LASMA instrument and this laser desorption mass spectrometer within MoMA instrument, that is, let's say, the closest what we are doing.
Yes, and then you have, of course, a lot of different techniques that we're being used, which typically rely on what we believe are more complex things like wet chemistry, where things need to be extracted from the soil or derivatized with a certain chemical reagent, which adds just a lot of complexity and sample preparation before you can do your measurements. But of course, this has found a lot of use in the past.
I see I have a question in the chat. Somebody is asking, what is the price of your product? I'm not sure if they are referring to the rover itself or the instrument.
So yeah, that's a very good question, right? So what we are designing is a very unique space instruments. So this instrument here we are using in origin was developed or started to be developed in 2003, so almost 20 years back. So if we say, and if we sum up all these costs, we are easily in the millions, right? That's because mostly of personal salaries, which scales that up. Hardware point of view, if we have just to redesign something like that from mechanical point of view, this is I would say a few thousands. But what is expensive behind is the knowledge. It's the knowledge why we designed it like this, and also the knowledge or the expertise how we need to operate the system. And that is the, I would say, the most expensive part behind the heritage about the instrument.
And from Rover point of view, it's actually also, let's say, in the
so okay, that's a very good point. So let's say we are selected for a mission on Europa, and we have to deliver a flight version, because what we operate in the lab, this is not a flight qualified instrument. So we need to vibrate the system, we need to freeze it to -50 degrees, etc. We need a lot of radiation shielding. Also there, we scale immediately to few millions. If we just follow all the steps, the verification tests, and then to have a flight version at the end. So we are not building like in industry thousands. But if we would do that, it's clear, and all the companies in industry have the same problem. As soon as you scale up the productivity, typically the design, the costs, they are lowered at the end.
Thanks a lot for this very detailed answer. I hope it answers the original question. I have another question. Would you like to tell us what was actually the most difficult part of the project this year? So you already told us about the most fun part, but what was the main challenge for you?
Yeah, that's a good question. Well, of course, in terms of the, well, let's say for me as a project manager, it was the most challenging part was time management. We're all full-time employed somewhere else, so either as a PhD or as a postdoc student. And the IGLUNA project is not something that can be done in like 1 or 2 hours per week. It needs serious dedication. So to find for everyone the time and to bring it all together, this was very challenging.
Yeah, and for me, the coronavirus, right? Because when we started to print the rover, we have absolutely not foreseen that something like that may happen. But as soon as that started, we had serious challenges to get the materials to print it. Mm-hmm. And it starts from the simple filaments and from the motors we needed to attach to the system, the electronics. And that was also a big question mark if we really can make it or not from Rover point of view of the functionality we need. Because we simply realized that we depend a lot on these supply chains, and they were affected a lot. Not only us, right? The whole society.
Well, that was great to see that even despite those challenges, you were able to complete the project. It was nice to see your rover completed. I do not see any further questions from our YouTube chat. We have a bit of time in case you would like to say a few more words.
I think we're good. I want to thank all the viewers. I hope you learned a little bit today about how to find life in space. And
and if somebody wants to have the designs to print the rover, just let us know. We are happy to deliver all the parts.
Great, thank you very much. Well, thank you, Team LDMS from Bern, for your very nice presentation. Thanks everyone for your interesting question that made this also a very nice discussion after the presentation. And we will have a talk from my guest a bit later today, so stay tuned for that. Thank you very much for watching us and have a nice day.
Thank you.